So here we have two blocks with given weights, and we have two static friction coefficients. And we're asked to determine how much force can we exert here. What's the maximum force we can exert such that this block configuration does not move? So same idea as the last problem, just more complicated because we have two separate blocks here. So I'm playing it out in my head, and one thing I envision if I try to push with that force is this block B could slide. That's one thing that could happen. But it could also tip about this point. But also I'm thinking this could be affecting A too. As I start bumping up this force, it could be enough such that A begins to slide as well. So I imagine that the whole thing might actually begin to slide as I increase that force. Or maybe the friction on this interface is so great and these two surfaces just don't want to let go that the whole thing wants to tip about this point right here. So my two other possible situations are the entire thing slips and the entire thing tips. So let's do the situation that B slips here. So looking at my FBD, I know I'm going to have gravity 100 pounds as the weight of block B. I'm trying to get this thing to move this way, which means my static friction is going to be acting this way. And because I'm saying that this is the situation where B just begins to slip, I can set that static friction to its max value, that just about to slip value, which will be a 0.2 times the normal force. The normal force will be moving over to the left this way, and of course I have all my dimensions. I also want to make sure I get that angle 20 degrees. So here's a horizontal line. Here's a continuation of that slant. So this is 20 degrees, which makes this red one 70 degrees. So I have an angle for the weight. And really that's the only angle I need because I'm planning to tilt my coordinate system. I will call X this way, and I'll call Y this way. And that red angle is the complement of that 20. It's 70. So if I do the sum of the forces in my X, I'm doing that because it has my force of interest in it. That force is acting in the negative X, and the normal force is acting in the positive X. And also I'm going to have a component of the weight acting in the X as well. And that's going to be 100 cosine of 70. And that is this component right here. Sorry that my picture isn't that good. But that weight has a component going this way in the positive X and a component going this way in the negative Y. All equal to 0. Two unknowns here, so we'll have to move on to the sum of the forces in the Y. I have the normal force which is acting 100% in the positive y direction. And the only other force with some sort of y component, is that weight, whose component is acting in the negative y, and we can grab it using the sine of that 70 degrees. So we'll solve for a normal force. We're basically getting a 94. And plugging that in for n here, we can figure out our pushing force that is needed to cause slipping. And that is a positive 53. So I'll put that on my force chart. For B to slip, our pushing force needs to be 53 pounds. Now, if our pushing force causes the block to tip, it's going to rotate about this point right here. And our normal force will be bunched up on that point. But of course we'll still have the friction, static friction, and the weight. But our geometry will be the same as last time. So in the case of tipping, the equation we usually use is sum of the moments about that tipping point. And it looks like only two forces will create moments, that pushing force and that weight. So it looks like my force will have a moment arm of 2, as this whole side is a 3 and this part is a 1. And that moment will be positive. Now the weight, its moment arm is going to be this distance here, and that looks like I'd have to create some right triangle and do some geometry to figure that out. So I'll just split up this weight vector into its components and do the moment of each component individually, because here's a moment arm for this component right here. That'll just be 1.5, half of that 3. And for my other component here, its moment arm will be this distance, which would be half of this 2.5. So those moment arms are pretty easy to calculate for these components. So I'll do this component first. So I have to grab it using trigonometry. So 100 cosine of that 70 gets me the force. And again, its moment arm will be this, which is just half of this 3. That'll be 1.5. That force wants to spin us this way, and that's going to be in our negative rotational direction. Our other component, I can grab it using the sine of 70. And its moment arm will be this distance, which is half of 2.5. Half of 2.5 is 1.25. And this force wants to spin us clockwise, which is in our negative direction. And the sum of the moments must equal 0. So I'll map that out, solve for F, and I'll get an 84.4. So to cause block B to tip, I need a force of 84.4. But we know that's not going to happen because as we increase my force here, we know we're going to cause B to slip before we get to the B tipping point situation. Now for the case that both of them slip, I'm treating them both as one single system, one single free body diagram, which means the normal force in between them, the one that I was really talking about in the previous free body diagrams, that's internal to the system, so I don't draw it. Same thing as the friction in between them. Of course, there's going to be friction in between them, because I push here, and this one wants to move, and it wants to drag this one along with it. But again, that force is internal in my free body diagram, so I do not draw it. Remember, I have to ask the question, what is externally touching the system here? So one thing is the normal force, which will be shifting over to the left. We have the friction between the ground and this crate A, and since we're talking about that this thing is just about to slip, I can set this as its maximum, which will be the mu s and that normal force. And of course I have my external pushing force. And I'll go with the same XY coordinate system. So I know I have to do some of the forces in the Y first to grab my normal force. Normal force is acting up in the Y direction. And I gotta grab both of those downwards Y components of my weights, and that'll be that. So I'll calculate that normal force to be 164.4, which I can then use in the sum forces in the X equation. Got my external force acting to the left, my maximum static friction force acting to the right, and my two X components of the weights acting to the right as well. And we'll get 158.5 for that F. So that is obviously not going to be the one to happen. It's way up there. And it kind of makes sense. Of course, if we want to move both of them, rather than just one, it's going to require more force. So I'm betting that this is going to be our answer, but we'll just play it safe and run that last possibility. So all I really have to do is change up my free body diagram a bit. This is just the static friction force now, which can really be anything. Here's our normal force concentrated at that tipping point, and that's about it. So I'll sum my moments about that tipping point. First I got my force, and its moment arm is going to be this distance right here. Remember, line of action of the force and the moment arm. That's going to be a 2 right here and a 3 right here to make a 5. So it'll be a 5 times our F, and that'll be a positive moment because my positive direction is counterclockwise. My two weights will be the only other forces that create moments. And like last time, I'm going to have to split them up. So here is the X one for that 75. So 75 cosine of that 70. Moment arm is going to be this right here, halfway up that 3. So it's going to be 1.5. Moment is negative. Then we have the other component, which I can get by doing the sine of 70. So 75 sine of 70 grabs me that force component, and its moment arm is going to be half of this length here, which is also 2.5. These two blocks are really having the same exact dimensions. So half of 2.5 is 1.25. Moment is also negative. And we have a similar thing going on for our other weight. So here's that first component. We'll do 100 cosine of 70. Moment number is going to be this entire red line. This red line is going to be 1.5, half of this 3, combined with this 3. 1.5 and 3 make a 4.5. Negative moment. And lastly, this guy right here, 100 sine of 70. And that momentum is going to be this distance right here, half of that 2.5. So we'll solve for that F, and we'll get a 79.6. So that's actually lower than I thought. That puts this situation really in second place here. But if we imagine starting that force off at 0 and increasing it, it is the B slipping with that force of 53 that happens first. So the answer to the question of determining the largest force F which can be applied without upsetting equilibrium, right at that threshold of 53 pounds. Alright, so I hope this problem made sense. If you have any questions, feel free to post them in the comments.